All right, page 96. Using the Hubble law without taking into account relativistic effects. And you'll see why we include this caveat. So let's just keep it simple for the time being. Let's say that scientists observe a galaxy that is 7 billion light years distant. Using the Hubble law, let's determine its receding velocity and express that answer as a decimal of c. So here's the Hubble law. Velocity equals the Hubble constant times the distance in parsecs. Our distance is 7 billion, or 10 to the 9th, light years. All right, so we're going to convert that into parsecs, so we'll divide by 3.26. And that gives us 2.147 times 10 to the 9th parsecs. So now, let's apply it. Our velocity is going to equal the Hubble constant, 71 kilometers per second per mega, or 10 to the 6 parsecs, times our distance, which we now know is 2.147 times 10 to the 9th parsecs over 1. All right, so right off the bat, we can cancel out parsecs. And 10 to the 9th over 10 to the 6th, that cancels out. This becomes 10 to the 3rd. And so now we have 71 times 2.147, and that comes out to 152.437 times 10 to the 3rd kilometers per second. So that number doesn't really jump out at us as being all that significant, but if we put it into scientific notation, something will pop out. So let's do that. I'm going to make that 1.524. So I move my decimal point to the left, and that means my exponent is going to go up, times 10 to the 5th kilometers per second. Okay, kilo, that's 10 to the 3rd, so that means I'm talking about 1.524 times 10 to the 8th meters per second. Now that number should ring a bell. Remember, speed of light, 3.0 times 10 to the 8th meters per second. So that's a fraction of the speed of light. So let's figure what that is. We're going to take 1.524 times 10 to the 8th. We're going to divide it by the speed of light. And we get 0.508 C. So that galaxy is moving away from us at a little over half the speed of light. It's important to know that that galaxy is not moving through space at half the speed of light. If it was, it would just get torn apart. But rather, space itself is expanding and dragging the galaxy along with it. It's kind of like raisin bread. Think about that. So if you're going to make raisin bread, you're going to make bread dough, and you're going to sprinkle in the raisins and mix it all in with the dough, and then you're going to throw it in the oven, and that bread is going to rise. So the bread dough itself is going to expand, and the raisins are going to get further and further apart. Now the raisins don't get any bigger, but they do get further and further apart. This is kind of what's happening. This is a good way to describe what's happening in our universe. Space itself is expanding, but in local areas where gravity is dominant, that expansion is overcome by gravity itself, and so the galaxies hold together gravitationally. So this is what's going on. And this is what we also know, is that when we look anywhere out there, whether from the northern hemisphere or the southern hemisphere, if we spot anything at that distance, 7 billion light years away, any galaxy that we spot at that distance is going to be moving away from us at that speed. Pretty amazing. Now, here's the first physics you ever learned in grade school. Distance equals rate times time. Therefore, time equals distance over rate. In other words, if you knew that there was an automobile moving away from you, moving directly away from you, and it was moving at 50 miles per hour constantly, and it was 100 miles away, well, you divide 100 miles by 50, and you'd know that that car had been moving away from you for 2 hours. Well, we can do the same thing here. We have the distance and we have the rate. So let's figure out how long that galaxy has been moving away from us. The distance, 7 times 10 to the 9th light years. The rate, expressed in terms of light, and that's what we're expressing here. Remember, it's a light year. That's a unit of distance. That's speed, that's time, right? Or rate times time, that gives us distance, okay? So we're going to divide it by 0.508 c. Now, remember, what does that refer to? It refers to the speed of light. What does that refer to? It refers to the speed of light, so we can cancel them right out. And so now we divide 7 by 0.508, and we get 13.78 times 10 to the 9th years. In other words, roughly 13.8 billion years. Well, we've just calculated the age of the universe. Pretty neat, huh? Now, we do have a problem. That is a relativistic velocity. And we know from previous discussions that when relativity is involved, we have to make accommodations for space and time. And that will be the next topic of discussion.